Hey guys, this is Agamapar Badyal, and this is my ALU circuit. So even though I didn't even get to a fully functioning 3x2 memory circuit, I still tried my best to explain all the information that I gathered off of this learning experience. There we go. What is an ALU? An arithmetic logic unit is a digital circuit that performs integer arithmetic and logical operations. The ALU is a fundamental building block of the central processing unit of a computer, also known as RAM. Mathematician John von Neumann proposed the ALU concept in 1945 when he wrote a report on the foundations of a new computer called the Exact. What is memory? Sorry. What is memory? Memory is the process in which information is encoded, stored, and retrieved. Encoding and registration, receiving, processing, and combining the received information. Storage: the creation of a permanent record of the encoded information. Retrieval, recall, and recollection: calling back the stored information in response to some cue for use in a process or activity. Bill of materials. So here we had our four main tools that we used in technology class, and then we had some of the main IC chips, including the NAND, XOR, OR, and AND. And then we had our special chip this time, which was dual D type flip flop with preset and clear. We also had another chip that involved our Schmidt trigger, and then we had our LED, our resistor, single pole double throw slide switch, a normally open push button. Some definitions for you guys here. A logic gate is an elementary building block of a digital circuit. Most logic gates have two inputs and one output. At any given moment, every terminal is in one of the two binary conditions as low or high, represented by different voltage levels. A low is the main power supply of the circuit. A switch, the device the device that opens and closes the circuit. Outputs and inputs which travel throughout the circuit. And some more here. A commercial D flip flop or a latch is a circuit that um, has two stable states and can be used to store state information. So the D flip flop the D flip-flop is widely used. It is also known as data or delay flip-flop. The D flip-flop captures the value of the D input at a definite portion or of the clock cycle, such as a rising edge of the clock. That captured value becomes the Q output. At other times, the output Q does not change. So here we have some of our gates and truth tables. Um, these are some of the gates that we use. So and, or, not, land. Um, there's the NOR gate in there, but we didn't use that. And there's the XOR. And yeah. Here we have our waveform for our Ruby flip-flop with preset and clear. And we have a schematic of the actual flip-flop at the bottom and how we can see um, going from the NAND 1 to NAND 2. That's how we see the word flip flop used into it. It's like basically an interchanging switch or a gate that we can say. And here's a layout of the schematic um, that we started off with. So here we have our beginning D flip flops over there. And these are the end one, which led to our LEDs. And here we have our switches for the load and the add. Over here we have our switches for the A0, A1, and A2. Over here are B0, B1, and B2. And here in the middle here, this was the most complicated part, as you know. There are the half adders and the full adders. And just to show you over here, this is how I ended off with my schematic diagram, going through each layout and highlighting. So somewhere here, maybe I might have gotten a flaw and defect where I couldn't have where I messed up my wiring, or maybe it's even just it's most likely my wiring, which probably don't have me at the stage that I wanted to be at, and yeah. And this is my process in day one of my circuit, and as we move on here, day two, day three, this is my day four. Throughout the days, these were my process pictures that I took, and compared to other circuits, I realized that I had a lot of uh, space to spare. As you can see right over here, right beside the LEDs, the bottom LEDs, we had enough space to even put in another couple chips if we needed to. And my layout was pretty well structured. I kind of thought it over for a bit of time before actually laying it out. So over here I have my all my switches, my beginning sorry about that, my beginning D flip flop in here, and I have my switch trigger beside that right here. I have the push button for the switch trigger over here. I have the NAND gate, so for the load and the add enable. And I got the AND gate switches, so the A0, A1, and A2 over here, and then all the middle half, the half and the full adders right here, and they're all connected using bridges. And then the final D flip flops and the final OR gate, which is just an extra, I can fit into the middle of the system, the middle breadboard, sorry. And then our end flip flops, and then the LEDs, which work towards the end over there. So some of the terms: a half adder. The half adder adds two signal binary digits A and B. It has two outputs, sum and carry, described by S and C. A full adder. The full adder circuit adds three 1-bit binary numbers and outputs two 1-bit binary numbers as a sum and a carry. A Schmidt trigger, a circuit in which the output increases to a steady maximum when the input rises above a certain gate. D-bounce ensures that only a single signal will be acted upon for a single opening or closing of a contact. So some of the flaws, just to let you guys know here, even though I didn't have a fully functioning circuit, I tried to grab as much information as I possibly could, even off my peers, just to give you guys the knowledge of the circuit. So I found out that for the fourth bit, there is no input from the data bus B, feedback from the Q of the bit 3 in the accumulator, and there's a lot of rebound problems, which even I encountered even without a fully functioning circuit. And finally, the most depressing thing, that I did not have a fully functioning circuit. So more terms for you guys is bus is a communication system that transfers data between components inside a computer or between computers. Accumulator is a register used to contain the results of an arithmetic or logical operation. And that's the end of my presentation. Thank you guys for watching. I hope this helped you out for coming generations or coming students that want to learn about the 3 by 2. I hope this helped you, and for the ones that know, and I wasn't able to share the information that I needed to. I have you guys. Thank you so much.